Welcome back. This is the second segment in section 3.1. As you recall, last time we had a sort of a brief dialogue about pi and one method for determining its value. But at this point, I think I'd like to talk about, in section 3.1, we introduced this idea of the radian measure of an angle, which is sometimes, for whatever reason, people find this to be somewhat challenging. I don't really know why, because it's another way of expressing the measure of an angle, and in many cases is far superior to any other version, because it doesn't have any real units. I mean, it has a unit, but the unit is unitless. It's really kind of a measure of a ratio. So let me just make some statements here. So at this point, we have only really looked at one basic way to measure angles, and that measurement is the degree. Now, we've looked at degrees and decimal degrees. We've looked at degrees, minutes, seconds, but those they're still degrees in some sense. You know, it's just dependent on how you break up the smaller pieces of them. The principal issue with degrees is that is a unit, and the unit is kind of arbitrary. I mean, why have we selected 360 degrees equals a full rotation? Some of that's historical. The Sumerians used what was called a sexagesimal decimal system, which means that like each unit is 60 times the unit before. We have a decimal system 10 times. If you move a digit over by 1, you've actually created a multiple of 10 or a division of 10, depending on which way you go. The Sumerians had a base 60. So, you know, that's where timekeeping comes from, because it was just one more unit. You start with the second, 60 seconds is a minute. That's like 1 unit to the left or whatever. So that's somewhere where it came from. And since we talked about pi, it turns out that it's that equilateral triangle. The equilateral triangle has an angle of 60 degrees at every vertex. And so when you add them all up, you end up with 360 degrees. That's ultimately where that number comes from. But it seems rather arbitrary. And instead of talking about a measurement of angles using some kind of a protractor or some sort of shape, if you will, there is a proposed better way of doing that. So if you consider for a second, rather than using some kind of a artificial device that is split up into smaller and smaller pieces, but instead use basic measurements along a circle, you can come up with a better way of measuring an angle. So let me, this is, I believe, page 3 now. So consider an angle, and this is no different than the way we've had angles before. It doesn't have to be in standard position, but you know, maybe if it looks that way, it'll be great. So we're going to superimpose on this angle. We're going to superimpose a circle where the center of the circle coincides with the vertex of the angle. Okay, so at this point, you know, this angle has some measure. We could measure it by slapping a protractor up there or some kind of a measurement device that divides up the circle into smaller and smaller pieces, or we could simply measure this arc length with some kind of a, I don't know, like a flexible tape or something, and then measure the radius, right? This is actually a pretty easy way to pull this off. Now, it's not necessarily the most intuitive because a protractor seems like a pretty simple thing to use, but if you imagine these circles are extraordinarily large, maybe that's not as easy as it sounds. So the first thing we might want to do, and when you do this, the ratio between the arc subtended by the angle, and that's this little piece here, divided by the radius, is what is called the radian measure of the angle. okay? And the unit, quote, unit that's used is called a radian, R-A-D-I-A-N. But it's not really a unit because it's the ratio of two lengths, and so it's actually a unitless number. So why do we call it a unit? Well, it's to cue the reader that when you see something expressed with the unit radian, and so a radian is the measure of an angle when the arc subtended by the angle is equal to the radius of that arc. Okay, and so and then the abbreviation would be R, lowercase r-a-d period, right? So this is the notation, or it's like I said, it's not really a unit because it's a ratio, r-a-d. Okay, so the first thing we might want to do is to figure out how to convert from what we're comfortable with, or degrees, into radians. Well, note that if you were to measure the entire circumference, that the entire circumference is actually, well, recall that the circumference divided by the diameter, 2 times the radius, is equal to pi. So the circumference will be equal to 2 pi times the radius. Now note that when the, because of the way that this radian is defined, that tells you that a full circle, so a full circle or a full revolution the arc subtended is the circumference. And consequently, a full revolution is 2 pi radians. So this gives us a way to convert between degrees and radians, because we know a full circle, a full revolution is 360 degrees, and this other way of defining it, a full revolution, is 2 pi radians. So the two must be exactly equal to each other. So 360 degrees is equal to 2 pi radians. Consequently, one radian is equal to 180 degrees divided by pi. Okay, so there's our conversion factor. And one of the things that we're going to do is fairly quickly, we're going to just do some conversions in here. Now, we're not quite ready to start messing with circles because this is sort of the setup for this. We need to be sort of fluent in how to use radians and maybe look at the trig functions of some of these, because there is some challenge to that. And as we move on, the expectation is that you'll be able to convert back and forth between them. So let me start a new page here and just run through some example conversions. So this is 3.1, page 4. All right. So for example, let's convert I don't know, let's say 0 degrees, 15 degrees, 30 degrees, 45, 90 degrees to radian measure. Okay, so how might we do that? Well, first off, this, you know, the sort of the principal principal conversion that I've produced here was if you had something in radians and wanted to convert it to degrees, you'd multiply by this ratio. We're going to kind of go the other way. So 0 degrees should be pretty obvious. So 0 degrees is, we're going to multiply by the reciprocal of the ratio that I had before. So pi radians divided by 180 degrees. This is a pretty boring conversion because it turns out to be 0 radians, okay? But with some of these others that are a little more interesting, so let's say 15 degrees. Well, 15 degrees to make the conversion, 15 degrees times pi radians divided by 180 degrees turns out to be equal to pi over 12. Okay. And often you'll see in the textbook they drop this unit because, again, it's not really a unit. It is something to clue the reader into understanding that this number is actually a measure of an angle as opposed to some other kind of measure. So let's try another one. How about 30 degrees? Well, 30 degrees, making the conversion, pi radians over 180 degrees. This is equal to pi over 6 radians. Similarly with 45. This is equal to pi over 4 radians. 90 degrees. That's pi over 2. And notice, I'm not approximating these. At no point am I approximating these values. I'm just leaving them in terms of pi, which is precise. And really the way that you should become comfortable with this. The thing that, that students often have a problem with when they start working with radians is that they don't realize that there's at least two different modes that their calculator is in. When you start doing some of these application problems, it happens like every time. People will be like, well, I'm not getting the number that the book says this is supposed to be or whatever else. And the first thing I will say is, what mode is your calculator in? Is it in the radians mode? And I'm just going to show you real quickly on this TI 30XA that it's a little hard to make out, but right here, this is saying DEG. And that tells you that this is in the degrees mode, which means if I plug in a number and then hit one of the basic trig functions, it's going to assume that that number is in degrees. If I change, this DRG button cycles through a couple different modes. You'll notice that when I hit it once, it changed to radians. And now, if I plug in a measurement of an angle in radians, it will produce the right trigonometric values. Okay, so this is one of the main sorts of mistakes that are, I mean, it's a pretty trivial mistake, but it just results in numbers being completely wrong. Because as you may notice, if you just kind of do a quick calculation, 1 radian is about 57 degrees. And that's quite a huge difference. It's not like they're close to each other. They're just nowhere in the same ballpark. Okay, so what I'd like to do is just really quickly, because the only thing that's really left in this section is to use this sort of conversion to find some exact values of trigonometric functions. So for example, this is kind of the process I go through when I see a trig function where the argument is written in terms of radians, and they will drop the RAD every single time. So when you see this, an argument that doesn't have a degree symbol, you have to assume that it's in radians. So for example, what is the sine of pi over 3? What's its exact value? Well, if you go back to, if you do this translation the other way, you'll get that this is equal to sine of pi over 3, and in this case, times 180 over pi. This is the conversion that's taking place between radians and degrees, and this is equal to the sine of 60 degrees, which you know is equal to the square root of 3 over 2. Okay, let's try another one. How about find the cosine of 7 pi over 6? Well, again, we'll make, cosine. We'll make this conversion, 7 pi over 6 times 180 degrees divided by pi. Turns out that this is going to be 210 degrees. So this is the cosine of 210 degrees. Notice that that is going to be a negative SIGN. It is a reference angle of 30 degrees. So it will be, the numerical value is root 3 over 2, but it has a negative sign. So this is negative root 3 over 2. And let's try another one. We don't need to go into this too much because this is basically the same stuff you've done before. It's just now we're using a different argument. So let's just, I don't know, let's take the secant of negative 2 pi over 3. First off, we'll make the conversion. So this is secant of negative 2 pi over 3 times 180 degrees divided by pi. So this turns out to be negative 120 degrees. So secant of negative 120. That is quadrant 3. So the SIGN is negative. It's equal to the reciprocal of cosine of negative 120 degrees. The reference angle is 60. So the numerical cosine value of 60 degrees is 1/2. It's the reciprocal, so 2 with a negative sign. So this is equal to negative 2. And there's a chart in the textbook, I think, that lists all of the values. This is something you don't necessarily have to memorize, but you do have to be able to make these. If you don't memorize them based on their radian value, you need to memorize at least based on their degree value. And it's a multi-step process to get there, but it's something that's kind of an expectation. It may seem strange that we've moved to this new system of angles. You're like, well, why can't I just measure everything with degrees for the rest of my life? And there is a good argument for that. However, when you start taking a calculus class and you start taking what's called a derivative, it's really a pain in the butt when you have to take a derivative of something that has a unit. This degree symbol is a unit, and it creates all kinds of problems that are immediately eliminated by just using radians, because those are technically not a unit, they're a ratio. Anyway, so I think this is probably sufficient for section 3.1. Section 3.2 is just about, it is a little, basically about the same length as 3.2, but there's a little bit more detail, or 3.1, there's a little more details I'd like to go into, but I will see you in the next section.